In this video, we are going to explore the concentration of ions in solution. So this tends to be a more challenging concept for a lot of people because the question they have would be, why isn't the concentration of the solute, let's say it's an ionic compound, equivalent to the concentration of the ions in a solution? So the reason is because the compound, when dissolved in water, will dissociate into ions. So the idea behind this is dissociation. And when they dissociate, depending on the chemical formula of the compound itself, it's not always going to dissociate in a 1-to-1 ratio. So the simplest way to illustrate this is in an example. So here we have a question that says, what is the concentration of potassium ions in a 0.25 molar of K2, so potassium carbonate solution? So just imagine a simpler example where, let's say instead of 0.25 molar, you have this 1 molar of K2CO3. But what does K2CO3 do? It dissociates into 2 potassium ions and 1 carbonate ion. So if I'm trying to represent this in solution, let's say 1 moles per liter is represented with 1 formula unit of K2CO3. Okay, and I only have 1 liter. So when I'm drawing this, K2CO3 is a formula unit, right? It might look something like K I'm only going to draw 1, right? Because we are talking about 1 molar, and I said I'm using 1 formula unit to represent 1 molar. So when this is dissociated or dissolved into water, what is it going to look like in a molecular level? So this is going to dissociate into 2 potassium ion and then 1 carbonate ion, which is why if you have this as a concentration of your entire compound, once it dissociates, you get twice as much potassium ion. So the concentration of potassium ion becomes twice as much as the concentration of the formula unit itself. So again, if I'm using 1 compound to represent 1 moles per liter, then you look at this picture where there are 2 potassium ions. So the concentration of potassium ion in here, so square brackets represent concentration, would be 2 moles per liter. Right? That's if we start with 1 moles per liter of the compound. So the relation here is to multiply by 2. Right? So now that we know what the relation is, well, let's look at the specific numbers in this question. What is the concentration of potassium ions in a 0.25 moles per liter potassium carbonate solution? So that's the question again. And one way of doing this is, again, thinking about this question and saying that the relation is 2 times. So you can say that the potassium ion concentration is just going to be twice that of the concentration of the formula unit itself. 0.25, right? Which is equal to 0.50 moles per liter. Okay. Or this is the way that works if you really understand what's going on. But if you don't trust yourself, again, you can always use units to help you out. So this 2 is because there are 2 potassium ions in 1 formula unit of K2CO3. Or remember that we were dealing with mole ratios before? So instead of saying that there are 2 ions in every 1 formula unit of K2CO3, it's the same as saying there are 2 moles. Sorry, let's erase this. Okay, that's better. So instead of saying there are 2 potassium ions in 1 formula unit of K2CO3, it's the same as saying that there are 2 moles of potassium ion in a mole of K2CO3. So this is the mole ratio within the compound. Okay. So I'm saying that the second way of doing this is to start with 0.25 moles per liter. But again, this 0.52 moles per liter is referring to moles of the ionic compound itself. But that's not what we want in the end. The question is asking for concentration, so moles per liter, of potassium ions. So somewhere in here, we have to make the conversion from K2CO3 to K+. So you can actually use what we learned in Unit 3, the last unit, and say, so ignore the liters for now. Okay, so ignore that for now. And say, in every mole of K2CO3, there are 2 moles of potassium ions. So the relation is, again, 2 moles of potassium ions in every mole of K2CO3. So now look at what happens with these units. Moles of K2CO3 cancels, and you're left with moles of potassium ions, and the denominator is left with liters, and you still get 0.5. So this question will work both ways. Either you do this in your head, or you do this, and you can clearly see how the unit cancels out, right? And that should all make sense when you think about what's actually happening in the dissociation process. So now let's do a more complicated question. What is the concentration of potassium ions when 2 liters of 0.25 moles per liter potassium carbonate solution is added to 1.5 liters of a 0.2 molar potassium chloride solution? So you're dealing with 2 solutions being added together. Let me draw it out first. They both have, so here is my 2 liters of .25 molar solution, and then you're adding it to another solution, this time 1.5 liters of 0.2 molar solution. So back to what I was saying, they both have potassium ions in it. But when they dissociate in different ratios. Okay. So this will dissociate into 2 potassium ions. This will dissociate into each of these, sorry, will dissociate into one potassium ion. Okay. So, if we take a look at the big picture, at the end, what do we want? At the end, we want concentration of potassium ions, meaning after they are mixed together. So, if I draw another beaker, with both of these solutions together, actually I'll use green to represent this. What will you have in this solution? So the total volume of the solution will be 3.50 liters, because you have added 2 liters to 1.5 liters. So that is 3.5 liters. Again, you added those two. Right? And then inside, there will be potassium ions from potassium carbonate. There will be potassium ions from potassium chloride. And we have to consider both of them in our calculation. So the moles of potassium ions from both. And when you put those two pieces of information together, that will give us the concentration of potassium ions. So concentration of potassium ions, C equals N over V. That's the equation. C equals N over V. And I'm representing C, concentration of potassium ion, using the square bracket. And I'm specifying that the moles that we are specifically looking at is moles of potassium ions. Okay, and if you really want, there are, of course, in the solution, also carbonates, and also chloride ions. But the question doesn't ask you for that. So it's really irrelevant that we calculate those. And what we are really interested in is this. So in order for us to calculate moles of potassium ions, and we have to calculate this first. And we have to calculate this first. K plus from KCl. We have to calculate them separately. Okay, so moles of potassium ions equal to moles of potassium ions from K2CO3 and moles of potassium ions from KCl. If you look at moles of potassium ions from K2CO3, N equals C times V. But this is C times V of this solution. Okay? And then separately, we can also calculate the same thing of moles of potassium ions coming from our second beaker. So it's moles of potassium ions from this solution. So what we're doing is we're calculating moles separately, and then we're adding them separately, and then we're adding them together in the next step. K2CO3, 2 liters, 0.25 moles per liter. So N equals CV equals 0.25 moles per liter times 2.00 liters. So that's equivalent to 0.5 moles. But the other thing is you also have to remember to multiply by 2. Why? Because this concentration is not directly for K, potassium ion. This concentration is for K2CO3. And you have to remember that there are 2 ions in K2CO3, and that's how we multiply by 2. Kind of like what we did here, right? So that's how we multiply by 2. This one is simpler because, well, let's look at the numbers again. What were they? They were 1.5 liters, 0.2 moles per liter. So 0.20 moles per liter times 1.50 liters. So that would be 0.3 moles. And this is simpler because in KCl, your ratio is 1. So that gives you 0.3 moles of potassium. The ratio is 1 because there's only 1 potassium ion in KCl. So now that we know how many moles of potassium ion comes from each solution separately, when you mix them together, so this would be after mixing, we will get, I'm just going to do it in one step and hope that you'll follow, okay? The total moles divided by the total volume at the end, which is 1.00 plus 0.3 moles of potassium ion, divided by the final solution is 3.5 liters. Equals 0.37. I think this is 2 significant digits, because these numbers have only 2 significant digits. 0.37 moles per liter. So therefore, the concentration of potassium ions is 0.37 moles per liter. So looking back at what we have done before, we sort of analyzed the situation first, right? And we said that there are potassium ions from here, but also from this other solution. But what we want is the concentration after mixing, which requires us to calculate moles of potassium ions from here, calculate moles of potassium ions from here, so we get moles of potassium ions from both, and then divided it by the total volume after mixing. And then we went ahead and used the equation N equals CV to calculate moles of potassium ion. And we have to make some changes to this because the numbers they gave us is is concentration of K2CO3, but we know the concentration of K2CO3 only potassium ions. So in here, the one for K2CO3, we have to multiply this by 2 to get to the moles of potassium ions. Here, we didn't have to do that because there's only one potassium ion in KCl. If you didn't do this, what you're actually calculating, if you didn't do the multiplying by 2, what you're actually calculating is the moles of K2CO3. So in order to convert to K, you have to multiply it by the number of potassium ions in the formula unit. And then finally, we can calculate the concentration after mixing, which is the moles of potassium ions that we got from both of these. So 1.3 moles divided by 3.5 liters, which is 0.37 moles per liters.